Right, moving on to equilibrium then, which is the final part of this topic. So the Boltzmann distribution stuff I sent out a week or so ago fits in between the rates of reaction and this section. So when we're talking about equilibrium, the most important point to start off with is that we're talking about reversible reactions. And you should remember from GCSE that we can identify if it's a reversible reaction, because rather than having the normal forward arrow, it'll have this reversible sign instead. What we will focus on is looking at dynamic equilibrium. And what we mean by dynamic equilibrium is these 2 points here. So when we're in dynamic equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And that means that the concentration of the reactant and the products doesn't change. It doesn't mean they're the same as one another, but it means that they won't change. So that's what we mean by dynamic equilibrium. And what's important here is that that will only happen if the reaction is happening in what we call a closed system. And all that means is that nothing can escape. So you'd be doing it in a beaker that's closed, and there's a lid on it. If there's a gas being produced, for example, it's happening in a sealed unit. Or if it's liquids, it's happening in a beaker where nothing can be poured off, drained off. So a closed system. So that's what dynamic equilibrium means. And there's a principle that we talk about a lot when we're talking about dynamic equilibrium and the effects that changing things like concentration and temperature have. And the principle is called Le Chatelier's principle, named after the scientist who came up with it. And basically, I've written a posh definition here, but basically all Le Chatelier's principle states is that when you've got a system in equilibrium, and by system we're talking about a reaction, if you change something, like you increase the temperature, the position of the equilibrium moves to minimise that change. So if we've increased the temperature, the position of equilibrium will move to reduce the temperature. If you reduce the temperature, equilibrium will move to increase the temperature. And the best way to think about this is a bit like a seesaw. So if you're balancing a pen on your finger, for example, equilibrium is where the pen will balance on your finger. Now, sometimes, depending on what the reaction is, equilibrium might be slap bang in the middle, but it might not be. It might be that if we've got more over this side, the position of equilibrium has to shift in order to balance that out. The physics of that is fairly obvious. So that's what the position of equilibrium is. It's a sliding scale that we can move along here in order to make the reaction balance. And that's what you need to be able to talk about. So the different factors that you need to be able to talk about. So the first one is concentration. So imagine that we've got this reaction here. I'm just using for this example generic letters rather than an actual reaction. So if you've got A plus B and there's a reversible reaction happening, and in the forward direction it would make C plus D. So what Le Chatelier's principle states is if I increase the concentration of A or B, so if I added some more A and B into the beaker, equilibrium will move this way and produce more C and D to get rid of the additional concentration of reactants that you've added in. And likewise, if I added some C and D into the reaction, into the closed system, what will happen is equilibrium will shift over this way and start to produce some more A and B in order to keep the concentrations the same. Think back to that definition of dynamic equilibrium. The concentration of the reactants and products doesn't change. So in order for that to happen, if I bung some more of this in, the system's going to have to get rid of it. And that's all Le Chatelier's principle is stating. So if we think about temperature then, so here I've given you an actual example. So this is the Haber process. And you can see the enthalpy change for the reaction is minus 92 kilojoules per mole. Remember, this enthalpy change, if it's a reversible reaction, that's always relating to the forward reaction. So in the forward reaction, making the ammonia, it's minus 92 kilojoules per mole. And hopefully you can all remember that that minus sign tells us it's an exothermic reaction. So in the forward direction, it's exothermic, which means the temperature is going to increase. So if I did this reaction at a higher temperature, so I increase the temperature, remembering that this way, going from here to here, in that direction, it's exothermic. If I physically increase the temperature that reaction's happening at, Le Chatelier's principle tells us that it's going to want to reduce the temperature. So equilibrium will move in the endothermic direction, and I'll reduce my yield of ammonia. Now there's an interesting point here, because if you look at the reaction conditions for the Haber process, you'll see that in theory you would want to do this at quite a low temperature, because the lower the temperature, the more of this product, the greater the yield of ammonia will be. However, if you think about rate of reaction, what will happen to the rate of reaction at a lower temperature? So it'll be slower. So although decreasing the temperature will increase your yield of ammonia, it'll happen at a ridiculously slow rate. So actually in industry, if you're an industrial chemist or a chemical engineer and you're doing these reactions in industry, you use what we call a compromise temperature. And it's a compromise because you're compromising yield over rate. So you actually do this at a higher temperature, and although that means your yield of ammonia is slightly lower because the equilibrium's moved over here, it happens at a faster rate. So it's a bit of a juggle, it's a compromise between the two. If this reaction here had got a positive number telling me it was endothermic in this direction, so the temperature decreased in this direction, if I then increased the temperature, equilibrium would move further over this way into the endothermic direction. What it might be worth you doing if you get a question like this in the exam and you're struggling to visualise it is write endo and exothermic on your graph. So for this example I'd be saying that way is exothermic, that way is endothermic. So then if the question said to me which direction will equilibrium move if we increase the temperature, I could be thinking, okay, well, it's going to want to go in the endothermic direction, so equilibrium will move to the left hand side. Okay, for pressure, I'm going to use the exact same example. As with rates of reaction we talked about in the previous video, pressure, we're looking at things that are gaseous, so this is a good example. And to work out what's going to happen to the pressure, you need to look at the total number of molecules on each side of the reaction. So over here, I've got 1 ammonia and I've got 3 hydrogens. So there's 4 molecules of gas over on this side, and there's 2 molecules of gas over on the product side, on the right hand side. So if I increase the pressure that this reaction happens at, equilibrium is going to move in the direction with lower pressure. So if I carry out the Haber process at a really high pressure, equilibrium will move over here and it will produce more ammonia. If I decrease the pressure, equilibrium would move over here to the side where there's more gas molecules to increase the pressure. Again, there's a bit of a compromise to be made in terms of pressure. While the Haber process would like to be done at a really high pressure because it would produce lots and lots of ammonia, high pressure costs a lot of money. And the reason it costs a lot of money in industry is because the equipment required to withstand that pressure is very expensive. There's obviously much bigger safety concerns as well when you're using high pressure. So normally a compromise is used, but ideally you would want to do this reaction at really high pressure so that it pushes equilibrium to that product side. And then the final thing for equilibrium is the effect of a catalyst. This one's really simple because a catalyst has absolutely no effect on the position of an equilibrium. It will speed up the backward reaction just as quickly as it will speed up the forward reaction. It does it equally, so the position of the equilibrium isn't actually moved. All it will do is increase the rate. It won't have any effect on the yield. Okay, the only other bit then that's included in that, if you look in your textbook, there's lots of nice examples of how you can show equilibrium happening Scientists like to show it, chemists tend to show it using coloured reactions because it's really easy to see what's happening. So there's some examples of that there for you. And then the maths that's involved is calculating the equilibrium constant. So what you need to do for this is to memorise this reaction here. Square brackets just refers to the concentration. So some nice simple math, and there's a couple of worked examples for you there, and it tells you what the value of Kc means. So I would suggest looking at page 160 and 161, but there's 2-3 worked examples there for you to have a look at too, I think. So there's plenty for you to see, and there's the questions that I've just emailed as well.